down again. You can start.
Thank you very much, Carol. I want to thank Carol and Tom Ford very much for inviting me to talk here. And I want to tell you about some work that we've been doing, both experimental and theoretical. And as a bonus, that something came up much too late to go into the abstract, I'm going to give you something, tell you something that is as recent as only last week. The project that all this is about is on getting sulfur out of coal. Some work that's supported by the DOE. The paper itself, as I was planning to give it, is a cut-down, revised version of what I was supposed to give at the Colloid Symposium at Lehigh, and consequently it is just about to come out in print in the Journal of Adhesion Science and Technology under the title of Theory of Acid-Base Hydrogen Bonding Interactions and so on, Applications to Coal and to Graphite Surfaces. I'm not going to talk about the coal application. I'm not going to talk about how you actually use this to get iron pyrite out of coal, but that is covered more or less in the paper that will be in print, and I can discuss it separately later. But if we start out with the first slide, please. This is the kind of state of affairs that existed up to a few years ago. This is for the contact angles of various ranks of coal that have been polished in nitrogen and air. The angle is plotted against the percent carbon in the coal. At the left are low-rank coals such as lignite. At the right are the anthracite coals, and there is a fairly strong peak in the region of the bituminous coals. Now, this kind of graph has been available for, I don't know, 10, 20 years, and this is ordinarily interpreted as meaning that there is a range of the degree of hydrophilicity or hydrophobic behavior, whichever way you want to talk about it. That coal, as you increase the carbon content of the coal, they become more and more hydrophobic. Well, this interpretation in terms of hydrophilic, hydrophobic behavior is something which is really too simple. Next slide, please. Now, what my colleagues and I have been doing for the last few years has been interpreting wetting by resolving surface free energy into several components. This was based on the excellent insight of Fred Fuchs about a dozen years ago, in which he identified a solid surface free energy as having two components, an apolar component, which we call gamma SLW, LW for Lifshitz van der Waals. It corresponds more or less to gamma D. And the gamma AB is due to acid-base interactions. Next slide. The theory that we've been developing since about 1985, and which is reviewed in Chem Reviews in 1988, identifies there are two components for the acid-base component of the surface energy. And we use generalized acid-base theory that we have a hydrogen bond formed by a proton donor, a base, interacting with a proton acceptor, an acid. This is the Brunstad interpretation of acid bases. We can do this equally well in terms of the Lewis theory of acid bases, in which a proton donor is an electron acceptor, is a base, and conversely for an acid. So we postulate that there are two parameters, which are called gamma plus and gamma minus. Next slide.
Can you press the button?
Pardon?
The button.
Oh, good. A substance may be considered apolar if the apolar component is very much greater than either or both of the acid and basic components. For example, Teflon is apolar. Substance is monopolar if the gamma plus term is very much greater than the gamma minus, or vice versa. And an example here is chloroform, or a ketone or an ether. Substance is bipolar if both the parameters are appreciable. And each substance has three different surface parameters. The combining rules are given as the gamma AB is twice the square root of the product of the acid and base terms if the substance is bipolar, and 0 if it is apolar or monopolar. You may ask, where did we get this combining rule? Two places. One is out of a hat, and the second is that we found that the people who do molecular orbitals calculations seem to think that this kind of combining rule is very reasonable. It fits in with the molecular orbitals approach. Now, for interaction of phases, say a solid and a liquid phase, we have the geometric mean combining rule, which we've been using for about 30 years. But for the acid-base interaction terms, we have two quite distinctly different terms. And you notice that one of them is the plus minus, and the other is the minus plus. And then the LW component, the geometric mean component, the first equation up there gets interpreted in terms of surface free energy as the difference between two square root terms. Products, the difference squared. The acid-base term is the product of two difference terms. Square root of gamma S plus minus square root of gamma L plus times the corresponding thing in the L minus. You can determine these three components for a solid if you can measure the contact angles of three different liquids and solve the three simultaneous equations. You use one apolar liquid, such as methylene iodide, and two polar liquids, and the equations, the extended version of the first equation to include the acid-base interactions comes out as the second and third equations. And you can tell by inspection that we have, if we know the parameters, the gamma plus, gamma minus, and gamma LW for the three liquids, then we have three equations and three unknowns, and we can solve for the three components for the solid. To do this, we have to have a battery of liquids, have to have the data of the three different components for the three different liquids. All of this is discussed fairly extensively in the previous papers that we published, so I'll give just the results of it. An important fact shows up in the first line of the table of data, that for water, we have at the upper right corner of that matrix 25.5 and 25.5 for the gamma plus and gamma minus. This is a convention that we have to set up because we can't get absolute values of the gamma plus and gamma minus. We have to have all of our calculations based on the convention that the gamma plus and gamma minus are the same for water. We could set up the convention in other ways. Now you may wonder, does that make the whole theory, everything completely just conventional? Well, it doesn't, because the operational variables, the macroscopic variables, the gamma AB terms, the contact angle terms are independent of the convention that we use. We have since we're working on coal, we've used coal from various sources, 14 different kinds of coal, plus graphite from 2 different sources. And this is a typical result that we get. The water contact angle, advancing angle, on this bituminous coal is about 87, and the retreating angle is 28. We do this in nitrogen so as to minimize the oxidation of the surface. We polish the samples in nitrogen. We transferred them to a Ramey-Hart instrument cell in nitrogen. All that. Now, the curious thing right off is that we have a huge hysteresis of contact angle, about 87 minus 28. 40 or 50 degrees. For all of the coal samples that we've used, the hysteresis of the water contact angle was around 40 or 50 degrees. There was a corresponding hysteresis in the glycerol contact angle, and a corresponding hysteresis independent of coal rank, independent of the composition of the coal, for diiodomethane. From this, we calculate the surface energy components. The gamma LW is 39.8 and 49.8 for the gamma LW based on the retreating angle. The first of these numbers, the 39.8, corresponds to the kind of number that you get by a Zisman treatment of the contact angle, in which you measure contact angle as a function of surface tension of the measuring liquid. The acidic component is about 0, and the basic component 2.5. I'll later on give a preliminary interpretation of these numbers. Now, to jump the gun on the new material, I am going to tell you right now that we have a new interpretation of the retreating angle. It is just a germ of an idea, but it seems, as far as we've gone so far, it seems to be rigorous. A thermodynamic explanation of the retreating angle. These are the results we get for different kinds of coal. If you look in the lower batch of numbers, show that the gamma plus, the acidic component of the surface free energy, is around 0.2 centimeter per square centimeter, and is qualitatively independent of coal rank. The numbers based on the retreating angle are around 1.8, again, more or less independent of coal rank. These two, I should have shown you this one first, because I usually talk about it first. But this is the apolar component of the surface free energy. And we can see that all of the coals behave quite a bit alike. The two lines are really parallel to each other. And here is the acidic component, basic component, and the lower line ranging from around 10 for the lowest ranked coal, the lignite coals, down to very close to 0 for graphite. And again, there's roughly a constant difference between these two curves. This is a signal for me to go to the overhead. It occurred to me only last week, well, this didn't occur to me, my colleague Untitled Chapter suggested this in a telephone call a couple of months ago, that if you have a liquid-solid contact angle, the advancing angle for one liquid is the retreating angle for the other. Now that sounds like a pretty simple and very obvious, incontrovertible statement. But it leads now to further ideas about the contact angle. This is that in terms of the derivation, there's an unstated premise in the thermodynamic derivation of the Young-Dupré equation. The angle is measured through the advancing liquid. So, in the usual kind of derivation of the Young-Dupré equation, you advance a liquid over a solid, and you write down the thermodynamics for spreading of liquid 3 over solid 1, and you combine this with the Young equation, and you get the Young-Dupré equation, which we have all come to know and love so well. Speaking of thermodynamics in general, it's a dirty job, but somebody has to do it. Now, if we turn it around and say we're spreading liquid 2 over the same solid, and we're measuring the contact angle through liquid 3, now we get a different result. In terms of signs, 3 and the 1,3 and 1,2 interfaces are interchanged. So the free energy of spreading 2 displacing 3 is not the negative of the free energy of spreading 3 over 2. This is all based on the fact that there are 3 terms here. You cannot reverse the process and have the sign change. The sign of the free energy does not change. The magnitude changes as well. Net result then is that while we have Young's equation in this form for the liquid advancing, we have for liquid 3 advancing, we have a different form. This is for that was for liquid 3. This is for liquid 3 retreating. We get a different form. And liquid 3 advancing is liquid 3 retreating is liquid 2 retreating. And when we have liquid 2 retreating, we get back to the original friendly form of Young's equation. This means that the interpretation of the contact angle as a measure of the properties of a high energy component of a solid surface needs revision. And there's a nice job for a student who he doesn't know that he's doomed to do it, but he's doomed. Let's see. We'll go on to the slides again. It had to happen sometime. This is actually the interpretation of the chemical interpretation of the different contact angles. And basically, it is that the acidic component, thank you. The first line, which is that the advancing and retreating angles are probes for 2 different kinds of site. This is now obsolete. We have decided that there must be an irreducible minimum of hysteresis that is valid on macroscopic surfaces that are homogeneous, that are smooth, and are rigid, and where there's no diffusion problems, no problems of molecules turning over. So we revise the first two lines. We think that the gamma plus component is probably due to aliphatic or naphthenic sites, and that there may be the line D there is now obsolete. Line E is probably due to oxygen-containing groups, and that we possibly have carbonyls that are present. Maybe I should have left this slide upside down. This is just about the end of the show. So, yes?
5 minutes.
Go 5 minutes. Well, that's
4 minutes.
to go back to firmer ground. This is the kind of structure that we're talking about in the cold process, in that when you grind up coal, grind it wet, dilute it, dump in some pentane or any hydrocarbon, beat it up in a Waring blender, you get out a type of something that looks like black cottage cheese. And the interior structure of that is liquid bridges of water between coal particles. The outside has the oil-water interface stabilized by the coal particles that are sitting in the interface. And coal does this because it is hydrophobic. The water contact angle is something like 130, 140 degrees as measured through the water. On the other hand, iron pyrite, where the sulfur is, and clay, shale, silica, everything that's hydrophilic, has, instead of having barrel-shaped liquid bridges, has spool-shaped liquid bridges, or liquid bridges that are shaped like cooling towers. They have a wasp waist, and when you stretch them, the narrow part of the bridge gets thinner and breaks. So liquid bridges under oil between the hydrophobic particles are stable. They're at least stable until you stretch them till the contact angle changes, or until you get them into a wasp waist structure first. But the liquid bridges through the hydrophilic particles are unstable. As a result, iron pyrite does not form stable aggregates, and it's actually rejected by the aggregates. And this is the mechanism of forming of cleaning the iron pyrite and also most of the ash forming material out of commercial coal. This particular process in its present form was developed by Dr. Douglas Keller at Syracuse, and he has a plant at Syracuse that actually cleans coal at the rate of 15 tons per hour on this. So this is a case where we're actually doing some good. We have built a theoretical foundation underneath his coal cleaning process. Thank you.
It's time for about one question.
Just a quick question on the structure of the whole argument, and that is the square root mean relationship coming from quantum chemical calculations, could you just make one or two more remarks
Yes?
concerning that, how that can...
Nope.
No.
No, the quantum mechanics of it involves developing a three-body kind of bond. All of your quantum mechanics, so Linus Pauling type of stuff, is based on having electrons in between two bodies, two heavy particles. If you have a third particle, a hydrogen atom, a proton, in between two heavy atoms, say two oxygen atoms, then the quantum mechanics, talking about in terms of pi bonds and sigma bonds and all that, no good at all. You can't use the old-fashioned, the perfectly reasonable molecular atomic orbital and molecular orbital approaches at all. So we have to take the quantum mechanician's word for it. I do anyway.
Thank you very much, Bob. Next paper will be given by Professor Keith Hall, who received his